Ever wondered how AI models like transformers make sense of complex data? Let's dive into a fascinating study that reveals why attention mechanisms, those clever focus switches in AI, can outperform traditional methods under certain conditions. So imagine you're trying to guess the average height of people in a room. If you only measure one person, your guess might be way off. But if you measure lots of people and average their heights, you'll get a much better estimate. This is the basic idea behind what researchers call variance reduction, using more data to make smarter predictions. Now picture a machine learning model trained on a Gaussian mixture dataset. That's just a fancy way of saying the data has clusters, like groups of points scattered around two different centers. The study fixes a specific temperature parameter, think of it as a control knob for the model's sensitivity, and compares two approaches, a traditional optimal quantizer and an attention-based predictor. Here's the twist. As the model gets more data points, longer input sequences, the attention mechanism surpasses the traditional method. Why? Because it doesn't just look at one data point. It aggregates many random samples from the same cluster. This is like asking a crowd of people to guess a value instead of just one person. The crowd's average is usually more accurate, right? The math shows that, in the long run, the attention model's risk, a measure of error, approaches a value tied to the dataset's complexity. Meanwhile, the traditional method can't keep up. The researchers call this a surprising result because it challenges assumptions about how these models should perform. But there's a catch. The attention model has an edge because it's not just guessing based on a single clue, it's leveraging the entire sequence. This suggests that attention mechanisms might be better at uncovering hidden patterns in data, especially when there's a lot of it. This work isn't just theoretical. It hints at why transformers, and their attention layers, excel at tasks like language understanding or image recognition. By focusing on patterns across many data points, they're essentially doing what humans do, learning from context. So what's next? Researchers want to see if these principles apply to even more complex models and real-world data. After all, the more we understand how attention works, the better we can design AI that truly learns from experience. Thanks for watching. If you're curious about how these ideas connect to everyday AI, hit subscribe. And let me know in the comments, what other mysteries of machine learning should we explore? Imagine you're trying to find the lowest point in a hilly terrain. But here's the catch. The hills are twisty, there are plateaus, and some spots look like valleys but aren't. In math terms, this is called a risk function, a way to measure how bad a solution is. The goal? To find the minimum risk, like the bottom of the valley. But how do algorithms know where to go? The secret lies in critical points, special spots where the slope of the risk function is flat. These can be peaks, the top of a hill, valleys, the bottom of a valley, or saddle points, like a mountain pass that's a peak in one direction but a valley in another. The paper we're looking at shows that under certain conditions, algorithms always end up at specific points. The corners plus or minus 1, the edges 0 plus or minus 1, and plus or minus 1, 0, or the center, 0. Here's the cool part. The math proves that most of the time, the algorithm avoids the bad spots. For example, the center 0 is a maximum, like the top of a hill. If the algorithm gets near there, it'll quickly slide away. Meanwhile, the corners plus or minus 1, are the true minima, the bottom of the valley. The edge points like 0 plus or minus 1 are saddle points, tricky spots where the algorithm might pause but eventually keeps moving. Why does this matter? In machine learning, these points determine whether an algorithm succeeds or fails. If it gets stuck at a saddle point, it might never find the best solution. But the research shows that with the right conditions, like a small enough step size, the algorithm guarantees convergence to the correct minimum. It's like having a GPS that always guides you to the lowest point, no matter how twisty the path. But here's the twist. The math isn't just about finding the lowest point. It's about understanding the terrain. By studying these critical points, researchers can design smarter algorithms that avoid pitfalls and find solutions faster. It's like knowing which trails are safe and which ones lead to cliffs, so you can hike smarter, not harder. So next time you interact with AI, remember, it's not just guessing. It's using elegant math to map out the risks and rewards of every decision. This work is a tiny piece of that puzzle, but it highlights how precise and powerful optimization can be. Ever wonder how machine learning models stay sharp when dealing with messy, complex data? Today, we're pulling back the curtain on a fascinating concept called risk, the secret ingredient that helps models like transformers learn what truly matters. Let's break it down. Imagine you're trying to predict the weather using clues like cloud shapes or wind speed. The risk here is like your average error, how often you're wrong over time. Now picture a perfect model, an oracle that knows the absolute best way to make predictions. This research asks, how wrong would this perfect model be under different conditions? The answer lies in breaking down risk into parts. Think of it like a puzzle. Each piece, labeled I0, II0, III0, etc., represents a factor affecting error. Some pieces depend on noise in the data, sigma, the complexity of the problem, d, or how much data we have, l. But here's the twist. The study shows that as data increases, the risk of the attention model converges to a lower bound tied to the dataset structure, while traditional methods lag behind. This isn't just theoretical. It's a glimpse into why attention mechanisms thrive in real-world applications. By aggregating patterns across sequences, They mimic human-like contextual understanding. But the math tells us this isn't accidental. It's a fundamental property of how attention distributes and reduces error. So what's next? Researchers are exploring whether these principles scale to deeper models and more chaotic data. The takeaway: attention isn't just a buzzword. It's a mathematically grounded tool for navigating uncertainty. Thanks for watching. If you want to dive deeper into how AI learns from data, hit subscribe. And let's keep the conversation going. What other AI mysteries should we unravel?